Alright guys, so Chrissy and I decided to do problem number 9, and so we were given this picture right here and asked to find the magnitude and direction at the origin, and we were given a little extra information. The positive x basically goes a long way in the positive x direction, so we are going to treat it as positive infinity. This semicircle over here is positive lambda, and this little box is negative lambda. So to start this problem, what we did was we separated the semicircle from the line, and this is the image of the semicircle that you get. So you have our radius. We took a little section of it for our dq with our d theta, and then obviously our theta is right here. So to complete this problem, we have the electric field equation with our dq over r squared. You are going to want this in terms of theta, because that is your integrating variable. So we went ahead and listed dq as lambda d theta. So now we're going to go ahead and break this up into its components. So here the component y, I went ahead and just put k for the 1 over 4 pi epsilon naught because it's a lot to write repeatedly. We're integrating from 0 to pi because it's a semicircle. Again, we changed dq to lambda d theta over r squared. And because it's in the y direction, you're multiplying by cosine of theta. So when we go ahead and integrate this, you get that it's k times lambda over r times sine of theta, because the integral of cosine of theta is sine of theta. And we're still integrating from 0 to pi. And when we do that, you get that the sine of pi is 0, and sine of 0 is also 0. So this part, your y component, it ends up being 0. And that makes a lot of sense because if you look here, it's even on the positive y and the negative y axis. So these would just end up canceling it out. I just showed you the math to make sure that we were right in that regard. For our x component, again, I just put k here for the 1 over 4 pi epsilon naught. We're still integrating from 0 to pi. Our lambda d theta over r squared times sine of theta. When we integrate, we have k times lambda over r. The integral of sine is negative cosine of theta. And when we go ahead and integrate that from 0 to pi, negative cosine of pi is 1 minus the negative cosine of 0, which is negative 1. In the end, we get that the magnitude of the semicircle is 2k lambda over r. We're going to come back to that one. We're going to move on to our line over here. So again, we picked our little slit of dq. These variables underneath here are arbitrary. I just picked 2 random letters. I like p and r. They're pretty. And the p here we're not going to really worry about because that's where our semicircle was in the previous part of the board. So we have our electric field equation again, 1 over 4 pi epsilon, integrated with the integral of dq over x squared, because x is our integrating variable here. Obviously, if we're integrating over x, we want our integration to be in terms of dx, so dq equals lambda dx. We're going to go ahead and plug that in here for our x component. As you can see, the line is residing only on the x-axis, so there is no y component to look at. So our x component, again, too lazy to write all of this out, it's just k over the integral from r, which is where it starts because everything before this was done in our semicircle part, to infinity, which was given to us in the problem that it goes on forever, of lambda dx over x squared. When we take the integral of that, we get k times lambda over x integrated from r to infinity. When you put infinity on the bottom, you get 0, indefinite integral, minus k times lambda over r. So in the end, you get negative k times lambda over r. So those are our 2 pieces. Here's the answer for the line. Here, once again, is the answer for the semicircle. And when we put it all together and add them up to get the overall magnitude, we find that you have your 2k k lambda over r subtracted from 1 k lambda over r. And so you get that you have 1 k lambda over r. I'm finally going to write out what k is again. So it's 1 over 4 pi epsilon naught times lambda over r, which is the answer that we were given. And that is how you solve number 9.